Good afternoon, good morning, good day to everyone on the line with us. This is Burke Callwhite. I'm the Executive Director of the American Academy of Environmental Engineers and Scientists, and we are your host for this continuing series of webinars which are based on our Excellence in Environmental Engineering and Science competition and awards that we do every year. Today's presentation is from the Grand Prize winner for research. It is a highly technical presentation from the other ones that I've seen, and we have a three-part team of speakers, so there's a lot of great information to be relayed. So let me run quickly through our speakers and go from there. Our first speaker, alphabetically, is Dave Becker, who is a geologist with the Environmental and Munitions Center of Expertise of the U.S. Army Corps of Engineers in Omaha, Nebraska. Since coming to the Center of Expertise in '91, Dave has been advising and providing guidance on field studies and in situ remediation products. He's been active in optimizing hazardous waste cleanup since 1997 and has led or participated in more than 65 studies for a variety of government and non-government clients. Dave's academic background, he's got a bachelor's degree in geology from the University of Nebraska at Omaha and a master's degree in geophysics from SMU in Dallas. Look forward to hearing from Dave. Our next speaker is Larry Deschaine, who is a principal engineer at HydroGeoLogic, Inc. Dr. Deschaine is a computational optimization expert with over 30 years of experience in the environmental field. In 1997, he received a Hammer Award from U.S. Vice President Al Gore for business process optimization. His award-winning doctoral research produced a self-adaptive universal modeling algorithm that first formally integrates human expertise, real-world observations, physics, engineering, and social models, and then automatically writes a descriptive equation of the system. Dave's academic career began at MIT, and he earned a doctoral degree in optimization algorithms research from Chalmers University of Technology, which is a Swedish institution. Our third speaker is Varut Guvanasen, who is Vice President of Research and Development at HGL. He's a modeling expert with over 30 years of experience in water resources and environmental engineering. Dr. Guvanasen has managed by the technical leadership for multiple projects in the U.S. and overseas, relating to water resources, nuclear waste disposal, and investigation. He got his bachelor's degree and Ph.D. in civil engineering and groundwater hydrology from the James Cook University in Queensland, and also has done postgraduate work at Lawrence Berkeley National Labs. So as you can see, we have some very distinguished, very knowledgeable speakers here for you. I'm going to step back and turn it over to Dave, Larry, or Varut. I forget who comes next.
It's actually Dave. Thank you very much, Burke. I appreciate the introduction. I have spent more than half my 35-year career focused on optimization of cleanups around the country. And it's really an honor for me to be able to speak with you today about my favorite topic, and that's remedy optimization. And what I want to do today is really provide a broad overview or context of remedy optimization so that we can see how the very fine work that HydroGeoLogic and their team has done in putting together the PBMO tool set. And so, I'm kind of laying a groundwork for everyone. And a good place to start is to provide a definition of remedy optimization. And I consider it any action that really goes to try to improve the protectiveness or effectiveness of the remedy, as well as to manage or reduce the costs associated with that. We obviously are trying to accelerate the attainment and closure of our sites, as well as manage those costs, and really it often comes down to, with optimization, a balancing act between cost and performance. And that concept of trade-off between cost and performance is an important one in optimization, and we'll hear more about that as we go through the presentation today. Let's go to the next slide. And let's just talk a little bit about, maybe some of this is common sense, but let's talk why we do optimization. Well, I would suspect that most of the people on the call today have clients or supervisors that are expecting us to do more with less, and we want to do as good of a job as we can to provide better protection of human health and the environment, at the same time, managing our clients or our programs' money as effectively as possible. In a lot of cases, we're also very interested in accelerating the attainment of site closure, so the property can be used for other purposes, or that it's just one less site that we have to manage. Another good benefit of optimization is that it typically leads to greener, more sustainable activities. We can really reduce our footprint and our environmental footprint through optimization. And for all these good reasons, it's been a popular topic since the late 1990s. Certainly in Department of Defense, my agency, many of the services, all the services have programs to implement optimization, or have in the past. The Environmental Protection Agency and Department of Energy have also had very good optimization efforts in the past, and certainly the private sector has been looking at this for many years, always motivated to look at that. Next slide, please. And let's talk now a little bit about where we can apply optimization in our cleanup projects. And even though initially the focus for optimization was on remedies that have been constructed and were operating, that was kind of the focus. There were big dollars associated with that. But over time, the realization has really come to most folks that optimization is something we should be doing throughout the life cycle of a cleanup project, starting with the characterization, through the design and construction, to the operation, even towards closure. So and a good example is that the Environmental Protection Agency has really embraced that concept of life cycle optimization and promotes it throughout all the different phases. So even though a lot of what we'll talk about today really gets at the long-term monitoring or remedy operation, can also be applied in design, but it's still, we should be thinking about it in the characterization phase as well. Let's go to the next slide. So I want to share with you, some of the lessons learned, some of what we consider the key aspects, and I think most of us practitioners in the optimization field feel are important aspects or points that a good optimization should include. And one of the fundamental things is that the optimization evaluation should be done by folks who are independent of the project team and have the experience and expertise to offer the latest state-of-the-art kind of ideas on how to make things better. The other key point really is that it needs to be a balance between improving performance and effectiveness, protectiveness, and reduction of cost. It can't all be just about reducing cost. It really is this balance or trade-off between those two and finding the sweet spot between those. A good remedy optimization, whether it's a qualitative or a sophisticated numerical optimization, really should start with the conceptual site model for the site. And that's why an independent team is good, because they can take a fresh look and develop their own conceptual site model and question some of the things that were taken for granted. And a conceptual site model is our mental picture of how a site operates, everything about what the source is, what kind of contaminants we have, how far they've been distributed, what the pathways are for them to be arriving at some exposure point. So, that's kind of a fundamental thing. Whether we explicitly think about it or not, we all do that. We create our own conceptual site model, and it's important for the optimization team to do that. The optimization should also be holistic in looking at not only what's going on now, but where does the site need to be. So we should look at the site ultimate goals and closure strategy, and looking at how appropriate the existing remedial or corrective action objectives are, looking at making sure that milestones for attaining certain concentrations or footprint or whatever size for the plume, have they been set, or what are realistic for those? What are the decision points for transitioning from, say, active remediation to passive remediation? Part of that would be perhaps, how to modify or tailor the monitoring program to fit the conditions that are observed, and then, looking at what are the criteria for actually declaring victory and closing the site out. Are those realistic? So that should be part of an optimization study. Next slide, please. So some of the sort of steps, or the checklist of things to accomplish with a broader remedy optimization. First is to look at the effectiveness of the remedy as it exists now. Is it achieving what it was intended to do in terms of either containing, preventing exposure to contaminants, or to actually clean up the contamination, reduce the size of the plume? Are the remedies in place actually addressing all the media, vapor as well as groundwater, soil, that would be appropriate. Have to make sure that all those things are being addressed. Obviously, with recent interest in vapor intrusion issues, that's a good example of where questions might come up that hadn't really been addressed before. And part of this evaluation may identify certain data that we don't have in order to make those effectiveness determinations. And so a lot of times the optimization identify additional data collection requirements in order to really understand if the remedy is being effective or not. Another key step in the optimization is the engineering evaluation. And we're going to look at what the treatment systems are, if there's active remediation like pump and treat or soil vapor extraction or something like that. Are there alternatives, tweaks, changes to the existing operation of the existing equipment that would make it better? Are there other components of a treatment train that could be more efficient or less costly, that we should consider maybe replacing some pieces of it? Or should we just toss the whole remedy and apply an entirely different technology because of the benefits it may offer in terms of reduced costs or accelerated cleanup? And one of the things I always tell people is that really, as an optimization team member, you want to look at anything that is not running at a condition that was assumed in design. Are the concentrations different? Are the flows different? Are the pressures or vacuums different from what was assumed in design? That's usually a flag that there's an opportunity for optimization. And so that would be part of the engineering evaluation. One of the key things with these kind of evaluations and the recommendations that come from them is, what is it going to cost? And can we justify the cost of implementing the change with cost savings down the road? And so you really need to have a good handle on what the existing baseline costs are for all the components. That's labor, utilities, materials, disposal, even management, so that you know where the money is going. That's usually a really good flag of what to focus on. You see where most of the money is spent, that's what you focus on with the optimization. And then you can use that as a basis to look at a change in cost for the recommendations that you're making. But one way or the other, you're going to have to estimate the cost for making any of the changes that you might recommend. Next slide, please. And it's inevitable that when you do these kind of optimization studies, is that there's usually some trepidation on the part of the existing project team. It's kind of an audit in their eyes. And so right from the start, the optimization has to be done tactfully. It has to be done in a context of team building and valuing everyone's input, and not just coming in and pontificating, I guess. So building a relationship with the project team can pay dividends in actually seeing the recommendations be implemented. They can buy in more readily if we do that. It needs to be pointed out to the project team that the alternatives that may be recommended may require bench or pilot scale testing to demonstrate that the work is as expected, or to finalize design parameters. And that, even if it doesn't pan out, it was still, based on the experience of the optimization team, worth trying because the potential benefits may have been large. So, it shouldn't be that the recommendations are a for sure thing. In some cases, we may tell them that they need to maybe try it out and see if it does work. Again, the costs that we give them for doing things have to be realistic, and that includes the changes in time to site closure or to different milestones also have to be relatively accurate in order to have credibility with them. Speaking of costs, based on my experience and others who have done a lot of these kind of studies, that for post-construction, operating remedies, that it's not unusual to be able to reduce costs by 25% or more, as well as to shorten the duration of the remedy with modest capital investments. Let's go to the next slide, please. Much of what I just got done talking about, can really be done in a lot of cases with just engineering or professional judgment and maybe some analytical equations, some very simplistic models, more or less a qualitative evaluation. But one of the really interesting and cool things is that there's a number of numerical tools, such as we're going to hear about today, that apply some very powerful concepts and algorithms to look at a lot of different combinations. And these can be applied to optimizing the remedy. For example, with pump and treat, it can optimize the pumping rates and well locations. These kind of tools can help identify the optimal time or milestone where you want to transition from one treatment to another, or how to have a treatment train set up spatially within a site in order to address multiple contaminants. These tools can help us evaluate that trade-off between cost and performance, or cost and time, so that we make a good decision about how much to invest in order to get the best benefit that we can from it, given certain constraints at the site. So these tools are very, very important, particularly at complicated sites, but not just limited to those. A good example is some of the numerical tools that are out there that have been widely applied, or those tools that have been used to optimize long-term monitoring programs. And I list here on the slide 3 of the common ones out there. MAROS is a very commonly used one, a couple other ones, GTS, 3TMO. These are public domain, free software that you can get online and use for your project with only modest learning curves. So we're obviously going to hear more about a very powerful tool that HydroGeoLogic has developed. Let's go to the next slide. So I just wanted to point you in the direction for more information, because obviously in 10 minutes I can't cover a lot of this stuff. But the Corps of Engineers has a website with some useful tools. I have checklists on there to help the optimization team ask the right questions, collect the right data, consider the right things in doing the optimization evaluation, at least qualitatively. There's some examples on the website, as well as some scope of work language in order to define what would be done as part of the optimization study. More generally, there's a couple of great websites there for optimization tools and guidance. The Federal Remediation Technology Roundtable optimization page is a wonderful resource, has a lot of different information from multiple agencies. And the CLUIN website that EPA manages has an optimization page that also is just wonderful. It's just rich with links to other good information. I direct you to those. If we can go to the next slide, please. So just to summarize, optimization for remedies involves a balancing act between effectiveness and cost, or time and cost, and is done to better protect the public and the environment, and to conserve our limited funds and resources. Optimization, though often thought about in the post-construction realm, is something that should be considered throughout the life cycle of the project. optimization in general should be done independently by an expert team, looking at the entirety of the project and from where it is now to where it needs to be for closure, looking at that closure strategy, should evaluate options to, everything from how the current system's operating to complete changeover technologies, and should have realistic costs associated with the recommendations. These optimization studies have been successful at reducing cost and time to clean up at many, many sites. So there's a demonstrated performance there and makes it worthwhile. And that even though a lot of the optimization can be done qualitatively with professional judgment, it can be done with very powerful quantitative tools, as we're going to hear about now. And at this point, I'm going to turn it over to the HydroGeoLogic team to talk about the PBMO tool set.
Well, thank you, David. As David indicates, we as an industry, we've had some successes remediating sites. However, they noted in that 2013 National Research Council report, there's a large number of complex sites that require cost-effective long-term maintenance. Now, HGL's PBMO supports this effort to resolve these design issues at the sites. For example, one thing that David was mentioning is that the subject matter experts, they can benefit from tools that can run hundreds or thousands of scenarios, as well as tools that are linked with optimization methods for remedial design, as well as the source identification of the plume delineation, the long-term management, including the treatment train designs. So the question really is, how can we as an industry go from where we are now to where we need to go? If we can remove the computational limitations together with providing an easy-to-use interface, well, this will allow the subject matter experts to explore more options, to evaluate options more closely, and to enable better informed decisions to be made. Now, PBMO facilitates these goals. Since many of the sites that do remain, they remain because they're difficult to remediate. And also there's new sites with emerging contaminants which are being discovered. So we still have these tough, very technical and managerial questions that remain. These really, in the nutshell, they're, how long will it take to remediate and what will it cost? And also, as stakeholders, how can we ensure that the best use of the stakeholder resources, the time and money, are being used wisely? For example, on these pump and treat remedies, some have been operating continually for many years or decades with little progress toward achieving these remedial goals. And some of the pump and treat remedies, they lack the exit strategies. As far as the cost, just to put this in context, there's hundreds of millions of dollars are being spent annually on just pump and treat systems. And with these emerging contaminants, one of the known effective remedies is pump and treat, this could lead to even more extensive use of the pump and treat remedies with the increased cost. Now, one thing David mentioned is like the traditional approaches for the remedial optimization. These can be efficient. They're not always bad. It's just the expert opinion may not have the quantitative foundation needed to get the global optimal solution. And sometimes the trial and error by the brute force model simulations, just using desktop computers, well, they're oversimplified model simulations, and they don't always achieve that computational efficiency. So let's learn from history. Historically, answering these questions accurately, it's been tough, and it's been limited by the insufficient tools and computational power. So how can we overcome these limitations? How can we design optimal site investigation and remedial strategies that meet the project goals? Such as the site investigation, the source location identification, the plume delineation and the tracking, the optimal long-term monitoring, all the while looking to minimize the life cycle cost while still maintaining the assurance to the stakeholders that the science is correct. For the remedial optimization, how does one control the plume migration? How does one optimize groundwater drawdown? Or how can we minimize or cap the cost of a remedial system, or minimize or cap the time it takes to clean up a site? How can we maximize or surpass the contaminant removal or the destruction goal? And really, all this is being done technically, while we still need to honor the property access restrictions and also the engineering constraints. Now, some of these goals are developed and published over 30 years ago, and they've been recirculated by many over the past several decades. But it's not until recently that we've had the computational capacity readily and economically available through the cloud computing. We could code and deploy these as computational optimization methods. So first I need to define what is computational optimization. It's a method that combines groundwater flow and transport models with mathematical optimization algorithms. And here at HGL, we've developed a cloud-based system that accomplishes this. It's improving the cost, time, and certainty of the remedial technology selection, design, and implementation. For example, we can provide optimal solutions for the remedy design, implementation, maintenance, and exit strategies. And we do this by linking our management optimization codes with the public domain software groundwater flow and transport models to ModFlow MT3DMS, and also our own ModFlow SurfAct. So to understand at least conceptually, the 30,000-foot view, this is a conceptualization of the PBMO system. It comprises of a medallion with two halves that house the groundwater flow and transport codes, that's in the lower half, and the numerous optimization methods, which is in the upper half. Now, supporting the user's interaction include the graphical user interface, or GUI, which is for the physics-based models, and also our optimization user interface, or the OUI, for the optimizers. Now, the stakeholders, the very important decision makers and influencers, can have impact and influence in the project at any stage. So in order to optimize remedial design, one needs to specify the objective functions, the decision variables, and the constraints. Now, what is an objective function? That's kind of an obscure term. Well, it represents a set of possible answers. For example, it could be the cost to remediate, or the time to remediate, or the mass removed. An example of this function is shown in the upper left, titled that 3D surface of multimodal objective functions. This is an actual surface, and it represents a cost to remediate the Umatilla site, which we'll describe later. Now, the optimization algorithm, this must be able to navigate these peaks and valleys, finding the optimal solution without getting stuck in a subpar solution. And there'll be more upon that later. So searching the objective function for the best solution, it's accomplished by adjusting the decision variables. These are the well locations, the pumping rates, where to put the injection locations. And we can only adjust the decision variables within the constraints imposed on the problem. This could be restrictions on well placement, such as land access use, the maximum pumping rate per well, or in total if we're looking at the treatment system, or maximum time for remediation looking at a property transfer, and the like. So the next slide discusses these various optimization methods available to PBMO to accomplish this. Now, looking at that objective function and understanding all the physical constraints and the complexities of the subsurface, we recognize that no one optimization algorithm is the best choice to solve every problem. So what we do in PBMO is that we interrogate the problem, assess its characteristics, we automatically select the optimization method suited to the challenge. So this slide here, this shows a subset of the numerical optimization algorithms that are available in the PBMO. Now, we also incorporate these groundwater flow and transport models by housing them in the lower half of this medallion. Now, these models are used widely in the industry. They include the ModFlow MT3DMS, our own ModFlow SurfAct. In the future, we're adding the ModFlow USG. which is for the unstructured gridding. Using PBMO's application programming interface, or the API, other models can be included, such as HEC-RAS, HEC-HMS, and MOD-HMS, which are integrated surface water groundwater modeling codes, which are critical for solving these water shortages that we've been hearing about in the news essentially every day. So how do we use PBMO? We can talk a lot about the technology and the algorithms, but how do we bring it to the ground? How do we get the user the tools and methods that they need at their location for their problems? Well, here's how it executes on the cloud. The analyst logs on to a private and secure web page, uploads the model files, configures the optimization problem, which is setting the objective functions, decision variables, and the constraints, and then launches the optimization system. What does PBMO do? It's all behind the scenes. It automatically configures the computing resources, it selects the optimization strategy, it solves the problem, and it brings the results, whether they be in process or at the end of the run, to the user, including report-ready format to look for management and stakeholder review. Now, what's happening behind the scenes, and as a user, you don't need to know this. I'll just explain what's happening to unveil the curtain, so to say. The PBMO system includes an optimization computational engine, or the OCE, and this orchestrates the analysis. So the project administrator determines the computational capacity plan, the grid, selects the optimization method or methods, and executes the run. So while this is occurring, the user can see and evaluate the progress via the OUI. So what's really happening now? We're on the Amazon cloud. We're running Ubuntu Linux. This slide is showing the grid engine in action. In this screenshot, we can see that under maximum CPUs, this particular grid has launched a grid capable of executing 4,096 candidate model runs in parallel. It has 934 models configured as runnable. That's in the upper bar there. It's starting 476 of them and is running 53. Now, just for your users, the PBMO handles all of this automatically. So the user need not be involved in any of these algorithms, any of this computational grid detail. This is all handled within the PBMO software. So, for example, if you're seeing this computational grid, and the worker queue, which is the number of candidate solutions, starts increasing, the PBMO system automatically expands the computational grid up to any limit that we define in order to meet the computational capacity of the demand. So with that, I'd like to turn this over now to Dr. Guvanasen, who will now discuss the PBMO system as experienced by the user, including case histories. Dr. Guvanasen?
Thank you, Dr. Deschaine. Now I will present PBMO Optimizer User Interface, or OUI. OUI was developed to facilitate the applications of PBMO in a cloud environment. It is a user-friendly interface for data entry. For example, decision variables, cost information, and so forth. It can also connect user with selected modeling codes in the cloud environment. It has an interactive dashboard that's updated in real time to visualize optimization results. It is also compatible with mobile browsers, so the users can use iPad or smartphones to monitor the progress or results of PBMO runs. Now I will present the highlights of the OUI. The OUI has 7 steps of data entry, as you can see on the screen, and you can monitor the progress using the status line in the middle of the screen right here. By the way, the name Fort Ord refers to a site in California that PBMO has been applied to, and we'll be talking about this site in another webinar in November. So you can see that at this stage we have completed step 3. We have chosen the model in step 1, defined contaminants in step 2, and we have chosen objective functions in step 3. By the way, there are three choices of objective functions: minimization of cost, minimization of cleanup time, and maximization of contaminant removal. Moving on, now you see that we have selected cost components in step number 4 and embarking on defining decision variables in step number 5. Step 5 can be divided into several management periods. And for each management period, we have to define well locations, rates, injection or extraction, cost, and well configuration. Now you can see that we have defined constraints in step number 6 and ready to review. At this stage, a summary will pop up. And once the details are satisfactory to you, you can go ahead and press the launch button at the bottom of the screen right here. And once you press the launch button, the data files and instructions will be sent to the cloud. And at this point, you can monitor the progress using the project dashboard. The project dashboard displays a number of outputs, including the 2 main graphs that you see on the screen. Let me first go through these 2 graphs. On the left is the objective function graph. In this case, it's a remedy cost versus scenario. Each dot on the graph represents a scenario. Results from the cloud will be returned to the OUI in batches. So this graph will evolve with time. On the right is the remedy performance graph, maximum concentration versus time. It's a comparison between the initial of the current scenario in light blue and the initial scenario in dark blue. Now, there are also other types of outputs, stack plots, tables, and individual bar charts. I'll show them a bit later. Now let's go through. If you hover over this graph, you can see cost information. By clicking on any scenario, the graphs on the right will be updated. By hovering on these graphs, you'll see concentration information. By hovering on these stack plots, you see individual component information. Now, by clicking on any scenario, all the plots will be updated. And you can also inspect details using tables. And individual bar charts. Now we have 3 application examples to present. For each example, we have animation that you can watch later at your leisure. For the links, go to our website and search for the word animation. Example 1 is a benchmark problem. The information comes from the Umatilla Army Depot in Oregon. The second example deals with complex pump and treat remedies design and implementation at a Superfund site. The third example involves optimization of dewatering and excavation at an open pit mine in Western Australia. This example is different from the previous 2 in the sense that it deals with water resources and conservation of natural resources. Now, let's begin with example 1. The information comes from the Umatilla Army Depot in Oregon. The site was established in 1941 as an ordnance depot. During the 50s and 60s, 85 million gallons of washout water laden with RDX and TNT was discharged into underlying lagoons, resulting in these 2 plumes right here. Now, that's a remedy in place design, as you can see on the left of the screen. The system consists of 3 extraction wells, EW1, 3, and 4. and 3 infiltration galleries, IF1, 2, and 3. Now, PBMO modified this configuration a little bit by removing these 2 components, EW4 and IF1, and replaced them with 2 extraction wells, PBMO1 and PBMO2, and these wells are located in the TNT plume. Now let's look at a comparison. This is a comparison between the remedy in place design results and PBMO optimal design results. You can see that there's a savings of $2.2 million, and most of the savings comes from labor costs right here, and there's a slight increase in capital costs. All other cost components are reduced. Now, this example demonstrates successfully the computational efficiency and robustness of PBMO. By using the public domain MGO optimization code, it required 5,000 simulations and 2.6 days of CPU time on the standard desktop PC. Now, using a similar PC, PBMO requires 127 simulations in 1.6 CPU hours. Today, using the cloud-based PBMO, we need only 60 simulations in 3 minutes. Now you can see that we have reduced the computation effort of optimization down from days to minutes, and thereby making practical what used to be just imagined. Example 2 comes from a site near Hastings in Nebraska. This is a Superfund site. The site is located right here. It's a 22-acre grain storage facility. Between 1959 and 1985, a grain fumigant consisting mainly of carbon tetrachloride was used at the site. And around 1994, contamination in soil and groundwater was reported. And subsequent investigations indicated that that's a long plume emanating from the site, and this plume is about 4 miles long. And now, it was afraid that private wells down gradient may be contaminated later, and that's also a TNT plume in a shallow aquifer hovering over the carbon tetrachloride plume. A groundwater flow model and contaminant transport model was developed to mimic the transport of the plume, to look at the migration of the plume and to assess the various remedial options. The model itself is 3-dimensional. It has 11 layers to mimic the local hydrogeology, and it has over 1 million cells, so you can see that it's quite a large model. The blue lines, these blue lines represent the outline of the model. These green dots represent candidate well locations, extraction wells. There are more than 4,000 of them. And these red dots represent candidate well locations or injection well locations. There are almost 100 of them. So the role of PBMO is to down select from these locations to come up with the best combination of number, rates, and locations of these candidate wells. Now also, there's another constraint. The drawdown cannot exceed 6 feet to prevent the TNT plume around here to be pulled down to a deeper aquifer. So you can see that, you can appreciate that this is a fairly big optimization problem because there are more than 4,500 decision variables and more than 2.2 million constraints. Now, PBMO down selected to 8 extraction wells, as you can see here, and 10 injection wells in 2 management periods. The first management period lasts 10 years, and the second management period, 16.5 years. The extraction rate for the first management period is close to 1,800 GPM, or gallons per minute, and close to 1,900 GPM for the second management period. Now I will show snapshots of how the optimal system performs. What you see are the two plumes, the depiction of the two plumes in 2019. The carbon tetrachloride plume in blue and the TNT plume in pink. These plumes are predicted locations in 2019 because the renovation is scheduled to begin in 2019. The green vertical lines represent extraction wells, and the red vertical lines represents injection wells. And you can see the cross-section at the bottom of the screen. 5 years later, you can see that the carbon tetrachloride plume is halted by the combination of injection and extraction wells. And 34 years later, you can see that the carbon tetrachloride plume has almost disappeared, but the tetrachloride plume still remains in the shallow aquifer. By the way, the TNT plume remains in the shallow aquifer. By the way, the TNT plume is beyond the scope of this remedial project. The third example comes from an open pit mine in Western Australia. The mine itself is located near Tom Price. It is an open pit mine. Its capacity is on the order of tens of millions of tons per year, and it has been in operation since the mid-2000s. There are 6 ore bodies or lenses at this particular area, at this particular site, spanning over the distance of 14 kilometers. And of interest is lens C and D. And the ore body is below. The challenge is that the ore body is below the water table. So the challenge is dewatering has to be done. The dewatering strategy was performed by a group of experts, basically an expert panel consisting of experienced engineers and hydrogeologists, as well as using calibrated groundwater models, came up with the best they thought possible for the dewatering strategy. Now, this is the plan view of the models used by the expert panel. The green line right here represents the outline of the ore body. These yellow dots represent candidate extraction well locations. There are 100 ex-pit wells and 13 in-pit wells. Now the expert panel came up with 26 locations in total. So the client wants to see whether PBMO could be used to improve on this solution or on this strategy. So this is what PBMO came up with. It requires only 17 wells, so 9 wells fewer than the solution offered by the expert panel. And of the 17 wells, only 11 is required to be in operation at any given time. On the left, you can see a system between years 1 to 4. Only 11 ex-pit wells are required. And on the right, between years 4 and 11, only 11 wells are also required at this point. You can see that we need only 5 ex-pit and 6 in-pit wells. Now, I'll show you snapshots of predicted performance of the PBMO optimal design. all the wells are color-coded. You can see exit wells in purple and input wells in yellow. Now, these are snapshots for years 4, 8, and 12. The blue surface represents the elevation of water table. And you can see, I hope you can see these small discs on this column represents the trackers of mine elevations. And you can see also that as the time progresses, the trackers and the water table deepen with time. And at any point in time, the water table is always below the mine elevation. This is a plot of cumulative groundwater extraction volume versus time. The black curve represents the it's based on PBMO solution, and the yellow curve is based on the expert design. And you can see that after 12 years, the PBMO solution results in 15.6 gigaliters in savings. 15.6 gigaliters is equivalent to 4.1 billion US gallons. Now, in summary, PBMO design results in substantial savings. It reduced the number of wells by 9, or equivalent to $4.5 million. It also reduced the total groundwater extracted by 15.6 gigaliters, or 4.1 billion US gallons, or $4.6 million. Now, all the restrictions relating to extraction well locations, groundwater levels, and mine schedules were not violated. And at this point, I'd like to pass on to Dr. Deschaine, who will talk about future enhancements of PBMO.
Thank you, Dr. Guvanasen. These real-life examples Dr. Guvanasen went over, these are problems with thousands of decision variables, millions of constraints. These are in the class called the Mixed Integer Nonlinear Programming, or the MINLP. And these problems are simulated by expensive models, the fully three-dimensional groundwater flow and transport models. These represent some of the most complicated and challenging environmental remediation problems ever formally optimized. Now, these successes, have motivated HCL to further extend our PBMO to include the site characterization, the plume delineation optimization services using the methods that we'll talk about that David had alluded to in the beginning. Specifically, we're looking to extend the PBMO to be applicable to the sites that have the limited characterization data, especially on the emerging contaminants where we're just starting the investigation, or these complicated sites that have the multiple plausible conceptual site models, sites that need to incorporate the treatment trains, that is, the multiple treatment technologies such as a pump and treat or the bioremediation with the bioremediation, sites that are operating under changing regulatory or stakeholder framework and variable abilities for stakeholder acceptance. So specifically, HCL is now including the source location identification method, the plume delineation and tracking methods, and also the optimal long-term monitoring algorithms. Next slide, please. So the first method I'd like to talk about is a source location identification algorithm. Now, determining the optimal identification of a source location, this is crucial for determining the nature and extent of groundwater contamination. And we can have sources that can consist of the DNAPL, the dense non-aqueous phase liquid, the LNAPL, the light non-aqueous phase liquid, and the emerging contaminants such as the PFAS and PFOA classic compounds. And these sources of contaminants can be emanating from an individual source or from multiple sources and may be interacting both physically and chemically. So let's talk about how this source delineation concept works. First, we do a historical record review, and the potential source locations are identified. Then a groundwater flow and transport model is constructed. You see the example on the left that includes the potential source locations. You can see that red bracket, and the likelihood of the column charts. So these are gathering the subject matter experts and the best available model of the situation, all in one place for systematic evaluation. Then you can see on the right-hand side, monitoring wells, those black dots, are sequentially installed until the actual source location is identified, as evidenced by that tall column, and the other source locations are eliminated. Those are the short columns. So by knowing where the source is, its location, strength, and duration, remediation is then focused on the critical source area, and hence the potential to misdirect remediation effort and cost is minimized. Now, this was actually developed by Dr. George F. Pinder's group at the University of Vermont. So I'd like to briefly show you a demonstration of the Indianapolis Source Finder on a real project. Now, this was applied to the Anniston Army Depot at Anniston, Alabama in 2009. This work was also conducted by Dr. George F. Pinder's group at the University of Vermont, and this was within the Strategic Environmental Research and Development Program, or SHRDP. Now, I supplied the team with a groundwater flow and transport model and other information, sampling, geology, etc. And in the previous example, the goal was to determine the source location, but this time in fully 3 dimensions. Now, the site is represented by a multi-layer model, the residuum overlying weathered bedrock. And on those 2 graphics, that layer 3, that represents the middle of the weathered bedrock zone. And the layer 5 is a residuum layer overlying the weathered bedrock. These contour intervals start with a TCE at the solubility limit. Now the solution, and you can see those columns in the lower left, they match the subject matter's expertise understanding of the source distribution. Time doesn't permit me to go into more details in this, so I've given you the report title, location, and you can go through this and the technology description by downloading the report off the web page. HCL is extending this technology to incorporate it into the PBMO. So the next method that I'd like to go over is the groundwater plume delineation and the plume tracking. Now, it's a tool that enables stakeholders and the decision makers to look at the plume migration and mitigation actions, but on a very solid informational foundation. So the tools that we're including into PBMO are, 1, an optimal monitoring well network design. And this is to develop a monitoring well network that optimizes and maximizes the information content of the plume, its shape, its geometry, its location in 3 dimensions at a specified point in time, like now, in 5 years, and 10 years. And we're also adding the algorithms for long-term monitoring optimization, which are taking the network, the optimal network, and applying it over a specified time horizon. So the information collected from a monitoring sample now at this time propagates into the future and is integrated throughout the entire system analysis. So knowing with certainty where groundwater plume is and where it's going enables the informed decision-making for the migration management strategies. So here's a case study of a TCE monitoring well assessment for the Ogallala Aquifer. It's an optimal monitoring well network, the design I participated in for the Department of Energy in 2002. The process consisted of conducting stakeholder reviews, and after that, the stakeholders looked at various technologies of how do we optimize this monitoring well network, because there's public drinking water wells down gradient of the site. So this technical advisory group, the TAG, which I was a member, recommended a customized tool for this monitoring well network evaluation. We deployed it. The technology assessed that the existing monitoring well network reduced the uncertainty of the not knowing where the plume may be migrating by 93.4%, An optimal one would reduce it by 98%. The optimal solution was obtained by including 1 or 2 wells strategically located, surgically located, versus the 6 to 12 deep wells that were originally envisioned by the stakeholders. All analysis and conclusions were accepted by the stakeholders via written signatory documentation, which showed the high confidence in analysis. And one thing that David mentioned is the cost, the realistic cost. And the analysis cost was $96,000, but it had a well installation avoidance cost of $2 million for a return on investment of 20 to 1. So to summarize this presentation, we've developed and are providing a tool that removes the computational limitations. It provides an easy-to-use interface to support the remedial design optimization. And this enables the subject matter experts to explore more options, to evaluate options more closely and easily, which provides for better information from which to make decisions. So it's a new paradigm for decision support. We integrate the management optimization with the physics-based models on distributed computing platforms to provide these real-time solutions. We've shown proven applications on pump and treat systems, new and existing ones, and we're also expanding the capabilities to provide the decision support on all aspects of the site, cradle to grave, for large, complex environmental restoration and water resource management challenges. So with this, I'd like to thank the American Academy of Environmental Engineers and Scientists for this opportunity to present our work. Now, if you have any questions or need any additional information, you either contact myself, Larry Deschaine, or Dr. Varut Guvanasen, or Mr. Jeffrey Fairbanks, our software manager at HydroGeoLogic. And we have a central email for this. It's pbmo@hgl.com. So thank you very much for your attention.
Well, thank you for taking the time to be with us today. I think we have a couple of questions possibly on the question and answer. Is that visible to you?
Can we see the queue?
I see one, yep.
Type of labor costs were reduced by PBMO?
And we're trying to read the questions at our end.
Okay.
The labor cost, are you talking about the first example, the labor cost coming mainly from monitoring and O&M, because from going from remedial in-place design to the optimal design will reduce the remediation time by a factor of 4, from 16 years to 4 years. So mainly in terms of O&M and monitoring.
Well, early on in your presentation, you guys mentioned that there was sort of a need to do some buy-in development among the various people involved in that. Is that a typical requirement when you go for complicated projects like this?
Yeah, this is Dave Becker. I'll weigh in on that. It really helps if you develop a rapport with the folks involved with the project, either on the team, that the client has, and possibly with the external stakeholders, the regulatory agencies and that. If you can have credibility with them and everything's clearly explained to them why you're recommending different things, and particularly if you show a balance between protectiveness and cost, you should have credibility with everybody, including those external stakeholders. And that the key is to make sure that they, are fully understanding the recommendation and don't view it as an attack on them. They're much more likely to implement your recommendations. Otherwise, there's always excuses and reasons that can be thrown up to say why you can't do something.
It's always easier to say no, right?
Yeah, right. Yeah.
I've got a question from Christian. Do you account for uncertainty in the model resulting? Yes, Christian, one of the analysis techniques we use is we can either use the deterministic model, which is the best optimally calibrated single model, or we also use geostatistical representation, GSLib, that can produce, if we have a variogram, either an expert-derived variogram or a data-driven variogram, that will provide for the uncertainty in the geological processes. We also can take the variograms and tie these to, for example, leaching scenarios. If we have a waste leaching pond that's a function of the connectivity underneath it, we're looking at different source loadings for different conceptualizations, either by geostatistically or different conceptual models. And then what we do is we look at the optimal solution approach given the uncertainties. We map the optimal components that are similar between all of the systems. Then we add, based upon our understanding of what may be the realistic system, which could be discoverable during the installation of a pump and treat or other aquifer stressing system. And then we'll add the components that make the most sense after this core system is designed. So it's a long answer, but yes, we do. Oh, you're welcome. Oh, what's this?
The question there from James.
No, the question is, how do you ensure you're creating an optimal remedial strategy for the site and not the physically based model due to parameter uncertainty? Okay, so this question is really asking the difference between model verification and validation. The verification is that we're computing the software correctly and how the software is working, it's coming up with an answer. Whereas the validation is that it's actually the right model for the situation. What that does is, for example, in the Fort Ord, which we'll be doing in November, it goes through the application of this technology to a site that achieved full site closure from the state of California. So it's a matter of, when you're validating a system, is to have the real physically based data with a physically based model. Now, sometimes it's hard to know the physically based model versus the data. So we use a technique called Kalman filtering, which adjusts between the weighting of the certainty between the data and the physical based model to come up with the optimal state estimate of the situation.
So I'd like to add that perhaps you can also use Monte Carlo simulation to do perturbation around the optimal solution to look at the range of uncertainty and risk level.
Okay, we have some requests for costs and funding and release dates. I'll leave that to our software manager. We're currently in the process of beta testing with half a dozen real key clients and customers to do the usability of systems. But Jeff, if you could get that.
Yeah, so we're currently in the integration testing phase right now for our software. We're finalizing the OUI, or the Optimizer User Interface module currently. And we're looking to release it probably sometime next year with 3 distinct service areas. The first one being that we would self-perform the work in-house, meaning that we would build the optimization task into a proposal and we would do that work in-house. The second being that a consultant or a government agency would bring the project to us, and we would work as a consultant or a subcontractor with that organization to complete the project. And the third is somebody who comes in trained, an organization that comes in trained, and they do the work themselves using PBMO and through the OUI, and with us available to assist as needed. And there was another question here, the time frame for compatibility with the integrated surface water groundwater models. That is sort of the next step. The next step is both the integrated surface water groundwater model as well as the surface water model, HEC-RAS and HEC-HMS, and also that's kind of the next step. And obviously our MOD-HMS tool, which is the integrated surface water groundwater model.
I'll just ask an ignorant question, if I may. That being, are there any particular application where this kind of software does not work well, or things that are more problematic than places you're currently working?
By working, do you mean the physics models or the optimizers? Or both?
Or both. Or both. Or to process others.
The optimizers are a class of general mixed integer and nonlinear programming codes. We've developed here. We've actually been writing these codes now for the past 9 years to develop them and tune them exactly to this field. So we've gone through enough of the case histories and the type of the mathematics that describe the physics that we're uncovering that we haven't had any site that we haven't been able to formally optimize, including the one with thousands of decision variables and millions of constraints. So from a numerical optimization standpoint, it's very solid, very robust. From the physics-based models, we're the developers of the ModFlow, shear factor and HMS, and Dr. Guvanasen is our in-house expert, and he's developing all the code, so that if you come across something that our current commercially available code doesn't work, just give Dr. Guvanasen a call, and he'll write the algorithm that maps it.
Yeah.
Go ahead.
We may have difficulties with some nonlinear models, for example, variably saturated models or density-dependent models. But in so doing, and at times you may find that some models may not converge, and that may lead to infeasible solutions. But OUI can also monitor the number of infeasible solutions that we may encounter, so that we may have to look more into the solutions and do some improvement on these models. But these are potential problems.
Well, I think we're about tight on time here, so why don't we wrap it up for this session. Thank everyone for logging on with us. Thank our speakers very much for fascinating presentation and really interesting technology there. And we look forward to seeing you guys again in the month of November, talking about the Fort Ord project.
Well, thank you very much, everybody.